This is a lesson about the amount of work that we do when we stretch a spring. So you were hanging mass onto the end of a spring, and the earth was using the force of gravity to pull that mass downwards. So there was a force applied to the spring, and the end of the spring moved a certain distance. And so, as in the diagram in front of you, we've got that there is a force, there is a distance, and we know from our work on energy that when a force moves an object through a certain distance, it transfers energy to the object in a process that we call work done. And we learned that there was a formula for this, and it's what's written on the screen in front of you, that work equals force times the distance moved in the direction of the force. In this particular case, the force is F, and the distance is how far the end of the spring has moved, which is the extension. So the work's just force times distance, which is Fx. And then because we know Hooke's law is F equals Kx, we can sub that in and we get that the work done is Kx squared. And then I've written at the bottom, do you agree with me? Do you think that is correct? So discuss. What do you think? Is it correct or not? Don't be shy. It is correct, says Frank. We have one vote for correct. Anybody else? I want to say yes, but it feels like a trick question. Indeed, it is. It's not correct. What's wrong with it? Any ideas? Well,
is extension different from distance?
Well, as long as the spring starts in its not stretched state, then the distance will be the extension. So that's fine. Something to do with the direction of the distance. No, that's fine as well. The force is downwards. The extension is downwards. So work really does equal force times distance. And the force really is F. And the distance really is X. Isn't it? Is that true? Take a closer look at F over here. What do you know about it that perhaps wasn't the case when we studied work done? Really? No ideas at all? So the force when we studied work done was just a number, like 10 newtons. Is that what's going on here? Why not, Henry? Morning, Cam. Okay, maybe if it because K is an unknown constant. No, we could carry out the Hooke's law experiment and we could find K. So we can know what K is. Okay, morning, Max. The X is the problem. Because when we pulled the spring down with a force F, the whole point of Hooke's law is that, well, to go through it again, the end of the spring is in equilibrium. So if we're pulling down with a force F, the spring must be pulling back up again with the same force F. Otherwise, the end of the spring wouldn't be in equilibrium. And therefore, at this point here, the force that the spring is pulling up with is given by kx. So it is only at this point that the force is F as given by kx, where x is this extension. A few moments before, during the motion from here to here, we were not having to pull the spring as much. To pull it down a little bit only took a little bit of force, then a bit more force, then a bit more force, then a bit more force, until finally, when we reach the actual distance s, only at this point are we actually using the force F equals kx, where this entire distance is x. When the spring had only stretched this far, we were only using half as much force, because this was half of the extension at that point. And so at this point, the halfway point, we were actually only using half of the force that we're using at the end. Bottom line is, this F isn't constant over the journey between 0 and x. And so it wouldn't be correct to multiply by the final force, because we haven't been exerting the final force for the entire extension of the spring. This will overestimate how much work has been done, because we were not pulling with the maximum force for the entire journey through the distance x. This is too big. So we need to be a bit cleverer about it. This formula is utterly fine. We just need to make sure that whenever we multiply by a distance, the force has not changed over the course of that distance. And that's the important thing that we've forgotten to do in just the algebra that I've rubbed out. Okay, so we've been here before. Do you remember any previous work we've done in the mechanics topic in which we needed to add up something while something else was changing? Do you remember us doing that? It was right at the beginning of the mechanics topic. Probably back in September. No, we didn't add anything up during the projectile motion. Good guess, though. Keep guessing. Okay, so it involved a graph. Time was on this axis. V was on this axis. We're doing velocity time graphs. And we said that the area underneath the graph was the distance traveled. Because for a rectangle, if this was, say, 3 meters per second for 4 seconds, then the distance traveled at 3 meters per second for 4 seconds was 12 meters, which happens to coincide with the area of this rectangle, which is 3 high and 4 wide. And so we adopted this notion that the area trapped beneath a graph was the distance traveled. But then when we had some acceleration, we couldn't just go multiplying this speed by this time, because that would give us an overestimate. We would work out this entire rectangle, which would have that little bit in it too much. And so what we did instead was we divided this shape up into a rectangle and a triangle. And that meant that we didn't overestimate this little bit at the top. So we've met this idea before, that the area beneath the graph gives us what we would get when we multiply one axis by the other, but it accounts for the fact if one of the variables is changing. And the reason why it works, if you remember, is because if we chop this up into a minute, tiny little shape that is extremely thin in terms of the time, then the error at the top is very, very, very small compared to the total area of the rest of the shape. And so if we just keep chopping this up into infinitesimally thin rectangles, then each rectangle is effectively like this, and the error at the top can be as small as we want. Remember, the word infinitesimally means as small as we want. So we can make the time at the bottom infinitesimally small, which means that the error will be infinitesimally small. And that effectively means we can ignore it. So if we chop the shape up into infinitesimally thin rectangles, then we will approximate the shape of the entire trapezium to a point at which we can ignore the error. Okay, so that's what we need to do here. We learned when we did the energy topic that if we drew a force time graph, then the area underneath the force time graph was the work done. But we restricted ourselves to examples in which the force was constant. Now what we've got is a completely different force time graph. You did a force sorry, keep writing. Sorry, the last one should have been, yeah, the last one should have been time because it was velocity time. This is a force distance graph. Right, our force distance graph is the one you drew last lesson. So it goes up like that. F equals kx. And so the work done over a minute, tiny little distance is the area of that very, very thin rectangle there, which technically is a trapezium. But if we make our time as thin as we want, then the tiny little triangle on the top of it will be infinitesimally small compared to the area of the rest of the rectangle. And then we just need to build this up infinitesimally thin rectangle at a time, bit by bit by bit. As we do that, we will build up to the area underneath the graph, which, because that's a diagonal line and that's a straight line, this is a vertical line always. You've just got yourself a right-angled triangle. And so you know that, well, let's not have the x. Let's just say for a final extension x with a final force F, then the work done is going to be the area underneath the triangle of base x and height F. So in actual fact, the work done is not Fx, it's a half Fx, a half base times height. And that's the formula that we need to settle on for the work done in stretching a spring. And then, as we did before, if we want to substitute in this formula, we can. So it's a half kx squared. Now, that's the work that we have done stretching the spring. We have put all of that effort in, and we have now gifted to the spring the potential to be able to do something. So, for instance, I could attach something to the end of the spring, like something light. And now when I let go of the force, so I suddenly stop holding onto the spring will do something. You know it will do something. It will boing back to its original shape. That's what you did when you unloaded it. the ability of the spring to change its own shape is what we have gifted to it with our work done. This spring can't do anything to its own shape. It just sits there all day long. It doesn't have the potential to change its own shape. But this stretched spring does. It's just waiting for me to let it. So as soon as I remove the force, the spring goes into action and does its spring thing. And so in a sense, when we have done work on the spring, yes, the force has deformed the spring, but at the same time, it has invested in the spring the potential for the spring to be elastic. And we refer to this as the elastic potential energy of the spring. So the elastic potential energy of any stretched spring is 1/2 kx squared. It is the work that was done stretching the spring in the first place, or compressing the spring if it's compressible, deforming the spring in the first place. And as long as the spring remains deformed, the moment that it is allowed by the force being removed to go back to the way that it used to be, there is an amount of energy that will be released back into the universe. And that might come out as heat. So the spring might get hot as it changes back to its original shape, might make a noise, but more likely it's going to provide some kinetic energy to whatever was attached to the spring. So this is the learning bit for today's lesson, that there is a formula for the work done stretching a spring, which equates to, once you finish stretching it, a store of energy within the spring. So you can think of it either way. This is the energy you put in to stretch it, and when you finish putting this energy in, the spring gets to keep it. So you can call it the elastic potential energy of a stretch spring, or you can call it the work done stretching the spring. It'll make more sense to do one or the other in certain circumstances, but the formula is 1/2 kx squared. Please do not forget the half. The biggest misconception that students make, or the biggest mistake students make, is to forget the half. Try to remember that it's a triangle, not a constant force. Okay, so in the textbook, we have been working our way through 6.2 this morning. It's just a single double page spread. And so I don't think it says anything that I haven't just said, but please feel free to reread it if you want to. And then there is a worked example which takes you through application of the formula. Quite often these questions give you some basic Hooke's law data from which you extract K, and then once you've got K, you use it to work out the work done, or the elastic potential energy. So there are 4 questions at the bottom of the page that I would like you to have a go at for the remainder of this lesson.